In this video, we are going to represent some basic and simple schemes that were used to transmit binary data. The first famous scheme that I'm sure that all of us know is the on-off. We call it on-off. And we call it on-off because the binary 1 is represented by a pulse, on, and the binary 0 is represented by no pulse. And we call it on-off return to 0. Return to 0. Why do we call it on-off return to 0? Because when we represent the 1 by a positive pulse, the positive pulse returns to 0 in the middle of the period. So if this is one period to transmit a bit, this is another period to transmit, this is another period to transmit a bit, you will find that the positive pulse, it returns to 0 in the middle of the period. And this return to 0, it has a benefit that we are going to explain later. Okay, so the first scheme is called on-off return to 0, where binary 1 is represented by a positive pulse, binary 0 is represented by no pulse. Another famous scheme is called the polar, where we represent the binary 1 by a positive pulse and the binary 0 by a negative pulse. And again, because the pulses, they go to 0 in the middle of the period, we call it polar return to 0. We can compare these two schemes to the on-off without return to 0. This is called on-off non-return to 0. Non-return to 0. And this is called polar non-return to 0. So this is on-off return to 0. This is on-off non-return to 0. This is polar return to 0. This is polar non-return to 0, because the pulses, they don't go back to 0 in the middle of the period. Actually, they continue until the end of the period. So this is one pulse that represents binary 1, and then it will be connected to the next pulse directly without returning to 0. That represents the next one, and then another pulse, and then when 0 comes, you're represented by a full width pulse. So the pulses, they don't go back to 0. Okay? What's the advantage of polar over on-off? The advantage of polar over on-off is in the power efficiency. How is that? Usually the bit error rate, the noise in unity, the bit error rate depends on the distance that you use between the binary 1 and the binary 0. The distance or the difference in amplitude that you use between the binary 1 and the binary 0. For example, if you use here 6 volt, and I'm going to use an even number here for to be easy and clear, let's assume that we represent binary 1 by 6 volt, and binary 0 is represented by 0 volt. The difference between the two levels is 6 volt, right? So the receiver basically will use these 6 volts, and it will put a threshold. So if the receiver receives something above 3 volt, above the threshold, then it will classify it as binary 1. If the receiver receives something below 3 volt, it will classify it to be binary 0. And then the receiver decides that this is binary 1, this is binary 0. So here the noise in unity is 3 volt. Why? Because if you transmit binary 1, you don't want the noise to increase or to decrease below 3 volt. If the noise is above 3 volt, is higher than 3 volt, maybe the binary 1 will be decoded incorrectly as binary 0. And if the noise is higher than 3 volt, maybe you get a noise, very high noise, then the binary 0 will be decoded as binary 1. So the noise in unity here is only 3 volt. If you want to have the same noise in unity in the polar, then you are going to have the binary 1 represented by 3 volt and the binary 0 represented by minus 3 volt, right? Now the difference between the binary 1 and the binary 0 is 6 volt, similar to the case of on-off. The difference was also 6 volt. But let's calculate the power in both cases, the average power. The average power here, if you assume that binary 1s and binary 0s, they have the same probability, 50% probability, then the average power here would be 36. This is if you transmit binary 1, you square the 6, it will be 36. And if you transmit binary 0, it will be 0. Then you divide over 2, then the power will be 18, right? On average. While here the power in the polar case, 50% you transmit 1, 50% you transmit 0, so 50% of the time you transmit power of 9, and the other 50% you transmit also a power of 9. When you square -3, it will be also 9, and then you divide over 2, it will give you 9. So the power in the polar case, the power is less than the on-off case. That's why this is power efficiency is considered to be an advantage for the polar case over the on-off. A third scheme is called the bipolar. The bipolar return to 0. In the bipolar return to 0, the 0 is represented by no pulse. As we see here, the 0, binary 0 is represented by no pulse, while the binary 1 is represented one time by a positive pulse, and then another time by a negative pulse, one time by a positive pulse, and then another time with a negative pulse, alternating. That's why the bipolar return to 0, sometimes they call it alternate mark inversion, or sometimes they call it pseudo-ternary. So it has two other names: alternate mark inversion, alternate mark inversion, AMI, or sometimes they call it pseudo-ternary. That's why, they call it alternate mark inversion, because the mark of the one is alternating between being positive and negative all the time. While 0 is not represented by a pulse, it's represented by 0. What's the benefit of this? What's the advantage of this over other schemes? The advantage of this scheme over other schemes is that the receiver can detect a single error. If a single error happens, then the receiver will be able to detect it. How is that? For example, assume that the receiver by mistake detects that this one is 0. This binary 1 that was transmitted as binary 1, due to noise, the receiver is going to detect it as 0. Then the receiver will find that he has, like here, binary 1 and binary 1, both of them with positive pulses, right? Then the receiver will detect that there must be an error that happened in the middle, because it's impossible to get a positive pulse followed by a positive pulse. A positive pulse should be followed by a negative pulse. So the receiver will be able to detect up to a single error, and then the receiver can go back and try to do a modified decoding or advanced decoding techniques to check where the error happened. So the bipolar return to 0, it helps the receiver to detect if there is an error or not. So it has some error detecting capabilities. Now let's talk about why the return to 0 sometimes is preferred over non-return to 0. The return to 0 is preferred over non-return to 0 because you can always extract the timing information from the return to 0. For example, let's focus on the polar signaling. I'm going to remove this. I'm going to remove what I wrote here. Let's focus on the polar return to 0 and the polar non-return to 0. If the receiver rectifies, when the receiver receives the polar return to 0, return to 0, and this is polar non-return to 0. If the receiver rectifies the polar return to 0, what does it get? Rectifies means it makes all the signal positive. So if the receiver receives the polar return to 0 and then it rectifies it, then the receiver is going to get something like this, right? Which is a periodic signal. And as we explained in one of the previous videos, that the regenerative repeater needs a periodic signal in order to extract the timing information, right? So if the receiver receives the polar return to 0 and rectifies it, makes it all positive, it will get a periodic signal, and then it can use this periodic signal in order to extract the timing information, right? Regardless of the sequence of ones and zeros, it doesn't matter. If you get a long sequence of ones, or you get a long sequence of zeros, or a mix between ones and zeros, if you rectify the signal, you will get a periodic signal always. That's why we say that the polar return to 0, it's a transparent transparent line coding scheme. Why transparent? Because it can extract the timing information regardless of the sequence of ones and zeros. The on-off and the bipolar. Oh, before we talk about the on-off and the bipolar, let's focus on the polar non-return to zero. In the polar non-return to zero, if the receiver rectifies the signal, then it will get a DC, right? So if the receiver rectifies this signal, makes it all positive, then the receiver will get a DC. And the DC, it's very difficult from a DC signal to extract timing information, because it's very difficult to know from a DC signal where is the beginning of the pulse, where is the end of the pulse, right? Where is the beginning of the period of one bit and the end of the period of this bit. It's just a constant, right? So it's very difficult to extract any timing information. And it is very difficult to extract any periodic signal from this signal that doesn't return to zero. That's why the polar return to zero, in the polar return to zero you can extract timing information. In the polar non-return to zero, you cannot extract the timing information. That's why sometimes we prefer the polar return to zero over the polar non-return to zero. However, you have to keep in mind that because in the polar return to zero, the pulse width is small. It's smaller than the pulse width in the non-return to zero. You expect that here the bandwidth will be larger. So yes, it has an advantage being transparent, but the non-return to zero, the bandwidth will be smaller. It has the advantage of smaller bandwidth. This is with respect to the polar. We can apply the same thing to the on-off and the bipolar. However, the on-off and the bipolar, you can extract timing information only if there is a good mix between ones and zeros. The sequence is a mixture between ones and zeros. You can extract timing information. Okay? And we can explain this. We can show that the on-off can be represented as a periodic signal in addition to a polar signal, added to a polar signal. And we can show that the bipolar signal, if you rectify it, you get an on-off which represents or which can be represented by a periodic signal plus a polar signal. However, these two schemes, although we can extract timing information from them, from the on-off and the bipolar, although we can extract timing information from them when we have a good mixture between ones and zeros, if the sequence has a good mixture between ones and zeros, but if you get a long sequence of zeros, for example, if you get here a long sequence of zeros, basically you are getting zero, right? If you get a long sequence of zeros, like 10, 15 zeros consecutively, you will get a 0 volt. And this 0 volt is like a DC volt 0 that you cannot extract any timing information from it. It's very similar to the polar non-return to zero. Same thing in the bipolar. In the bipolar, if you get a long sequence of zeros, you will not be able to extract any timing information. So, although on-off and bipolar, we can extract timing information, but it's not for any sequence. In some sequences, like long sequence of zeros, will not be able to extract timing information. That's why we cannot say that the on-off and the bipolar, we cannot say that these sequences are transparent. They are non-transparent, but although they are non-transparent, if there is a good mixture between ones and zeros, we will be able to extract timing information. Okay? So this is basically regarding the why the return to zero might be useful. It's for the timing information. There is another scheme called Manchester coding. In the Manchester coding, we represent the one by. In the Manchester coding, we represent the one by a pulse like this. This is binary 1, and we represent the 0 by a pulse like this. This is binary 0. This is called Manchester coding. And also it has some advantages. When we look at the spectrum of these schemes, you will see the advantage of Manchester coding. Now, in all line coding schemes that we discussed so far, we are using a rectangular pulse to represent the ones and sometimes the zeros, right? with different amplitudes, of course, positive amplitude or negative amplitude. And in the previous video, we saw that the power spectral density of any line coding scheme depends on the coding between the bits and on the pulse shape. So we wrote that the power spectral density, let me get the pen. We wrote that the power spectral density is the power spectral density of the coding between the bits multiplied by the Fourier transform of the pulse that we are using squared. This is what we talked about, we discussed in one of the previous videos. So the power spectral density of the line coding scheme depends mainly on the pulse shape that you are using. And here, since we are using a rectangular pulse shape, you expect that you are going to get here a sinc squared, right? So you expect that you are going to get sinc squared. And this is actually the case. I'm going to show you now quickly the power spectral density of some of the line coding schemes that we discussed. For example, here, this is the power spectral density of the polar signal. You'll find that it is a sinc squared. It goes from minus infinity to infinity. And the first zero, it happens here at 2 RB, where RB here, RB is the data rate, the bit rate. RB is the bit rate, which is equal to 1 over TB. If you assume that you are transmitting 1 bit every TB, then RB will be the bit rate. And here the first zero, the essential bandwidth will be 2 RB. Of course, we ask here the question, is that efficient or not? Is that efficient or not? We studied before the minimum bandwidth required to transmit a data rate with RB bits per second. And the minimum bandwidth was RB over 2. So the minimum bandwidth that you need in order to transmit a data bit rate of RB pieces of information per second, RB bits per second, is RB over 2. Here, we are not using RB over 2, we are using 2 RB, which is much larger than the minimum bandwidth required. So this is with respect, this is the spectrum of the power spectral density of the polar signal. Again, the most important thing to know here is that it will be a sinc squared because it depends on the pulse shape that we are using, and we are using here a rectangular pulse shape. And the rectangular pulse shape, because it goes back in the middle, it's return to zero. This is polar return to zero. It goes back with the half width. It goes back to zero in the middle of the bit interval. You will find that the bandwidth will be large. Let's see another one. For example, I'm going to show you here. This is the on-off return to zero. The on-off return to zero. It's again sinc squared because we are using a rectangular pulse. Again, it reaches 0 at 2 RB because it's returned to 0. It goes back in the middle of the interval. So you expect that the bandwidth will be doubled. Okay, it will be 2 RB hertz, the essential bandwidth. And then here it's very similar to the polar, except that we have some additional deltas. In the middle, we have some additional deltas multiplied or added to the sinc square. So we have a sinc square plus sequence of deltas. This is with respect to the on-off return to zero. And again, the power spectral density, theoretically, it goes from minus infinity to infinity, and the essential bandwidth is 2 RB. Let's see another one. Here, this is a comparison between different line coding schemes. You'll find that we have, this is the polar that we discussed before. It was sinc squared. The bipolar has an advantage of 0 DC. It has a 0 at DC, and we said before that this is one of the good things about any line coding scheme is you try to have a 0 DC component, because the DC, it doesn't pass through the communication circuitry. You can imagine that there are some transformers in the middle or something that will not pass the DC. So if you put the power on DC during the transmission, this power will not reach to the other side. It will not pass to the other side. So you are losing this power anyways. So it's more efficient. It's more power efficient to have a 0 at DC. Because if you don't have a 0 at DC, this power, that like the polar case, you don't have a 0 at DC, this power will not reach to the receiver, and hence you are losing this power, and this is not efficient. So it's a good thing to have in your line coding scheme to have a 0 DC. And this is satisfied by the bipolar and also the split phase. The split phase here is the same as the Manchester coding that we discussed before. Manchester coding. So this is Manchester coding. It's also called split phase. It also satisfies the 0 DC. However, the split phase, it has larger bandwidth than the bipolar. The bipolar, its essential bandwidth is RB compared to 2RB in case of polar, in case of on-off, in case of split phase. So this is basically the spectrum of the simple and basic line coding schemes that we discussed here. All of them, they use rectangular pulses, and hence you expect that the power spectral density will consist of sinc squared multiplied by some other factor due to the coding between the bits. And we saw a comparison that some of them they have 0 at DC, some of them they have large bandwidth, some of them their bandwidth is small. For all of them, theoretically, the bandwidth goes from -infinity to infinity, and this will cause a problem to us that we are going to discuss next. See you in the next video.